Hi, I'm Chris Brooks. I'm faculty here at the School of Information at the University of Michigan. I teach in our data science courses here, and I use Python heavily. And I work daily in Python and use this development environment called the Jupyter Notebooks. I'm pleased that I'll be able to share that with you through this course. The Jupyter Notebooks is a great piece of technology that allows you to use the web essentially to write real-world Python programs that leverage really impressive APIs, including optical character recognition and detecting faces and so forth. In my work here, I run a research lab called the Educational Technology Collective, or etc. And we do research in educational technology and learning analytics. I'm really interested in how students like yourself interact with technology like the Coursera platform, including the content, so videos like these, and your peers on the discussion forums. So my research is really focused on building things like predictive models of student success and studying how you interact in these different avenues to exceed learning expectations. In this course, we're going to be more project-based, and it's a little different focus than the previous courses. So in the first 4 courses in this specialization, you learn the fundamentals of Python. And now we want you to practice those fundamentals to try and solve a project. We're going to introduce to you new libraries. Now the goal here is not actually to learn those libraries in detail, but to learn enough about those libraries and moreover to have this meta-learning, to learn how to approach a new library so that you can start using your skills in the wild to solve the projects that you might be interested in. Those libraries are going to include image recognition libraries, so Pillow and image manipulation, Tesseract, which is an optical character recognition library, so how we take pictures of books and take the text out of them and turn it into something we can process. Kraken, which is a layout library for text, and you'll get a sense for the challenges that come when dealing with taking images and trying to recognize characters in them. And then the last one we'll introduce is called OpenCV, where CV stands for computer vision. And it's it's used for a lot of things, but we're going to focus on using it to detect faces in pictures. And your project will be about that. So one last thing to note, along with some of the other faculty here at the School of Information, I teach a data science specialization on Coursera. We use Python heavily in that in the Jupyter Notebooks. And we think that after you finish a course like this and come all the way through it, you're more than ready to take that specialization. So if you want to continue your learning on the platform and continue your learning with us, please join us in that specialization. Let's just dig into the class now. Hi, in this video, I'm going to share with you the Jupyter Notebook. The Jupyter Notebook's a great way to get started with Python on the Coursera platform. And it's a great way to do data science and other more advanced Python aspects on the platform too. So let's dive in and take a look. So when you log into the Jupyter platform, you'll be greeted with a screen that looks like this. Jupyter's really built around this notion of code cells. So here I have one cell. Now there's a full Python interpreter running in the background behind this, so I can do things like create variables. So here I'll just say x equals 10, and then we'll just print x. You'll see that there's no output until you actually go to run the cell. But when you run the cell, the interpreter returns you the result. You also get a little number indicating how many cells have been run. So you can see in this example, I played 10 practice cells before actually showing this. Now, after it runs, it's not like the application is finished running. The kernel is still running in an interpreter mode, and we can continue to send queries to it. So if we wanted to say x plus x, and we wanted to print that, you can see that prints out as we expected. If you wanted to, you can stop the interpreter. So if you feel that the state is confusing or you just want a fresh Python instance, it's actually pretty easy to do that. You go up to kernel and you say restart. And often I use restart and clear output as a way that reminds me that the interpreter's actually been restarted. You can cut, copy, and paste cells and move them around, and so you could do those normal kinds of things. The Jupyter Notebook has a special feature. It actually has a number of them, but one is that if the result of your last statement was an object, there was some value returned, but you don't do anything with that, it then automatically tries to print that to screen. A good example might be this. So if we say x equals 10 and then just the value x, and then we actually run that, we'll actually see the output. And so you'll often see in some of the videos people just leaving the value towards the end. You can individually run cells. For I in range 10, so if we want to have a loop, print I, we could actually just not run this yet. And we could say down here, wait, what was the value of I? And just run that individual cell, and oh, I is not actually defined. If we then decide we want to run that, okay, there's a bunch of I's, and now run this cell again, we could do that. So you can see that we can have a non-linear editing format. And that can be a little tricky, actually, because you could do things like change the value in one cell, but then, this seems to suggest that I should be 9, but then when we run it, we actually see that it's -1. So you can sometimes get this irregular state, or at least it feels irregular. It's actually the interpreter, the way it's run, that you've run the cells in order determines the interpreter state. And you can often see that if you look at the cell number here. So 6 is greater than 5, but it's greater than 3. So you can see that we were running some things in a different order. One of the benefits of the Jupyter platform is that you can add just text in here as well. So let's say I want to describe this is a great example of a loop. And let's say I want this section to even be called loops. So you can change the format of a cell here, and there's a number of different formats. And you'll mostly use code and then something called Markdown. And so when you change it to Markdown, you'll note that the in-out goes away because it won't be sent to the interpreter. But when you run the cell, it'll actually run it in a data format called Markdown. And so like the £sign here, or a double £sign means give me a title. So when you actually run that, you get a nice bit of text. And so you can actually mark up your code execution in a way that's a lot like a textbook might be. And so you could create a whole textbook in this environment. So those are the main features of the Jupyter Notebook. There are a bunch of other options. So one that I often use is I will restart and run all. So if I want to run all of the values in a notebook, I want to just see the whole execution trace, you can do that. So in this case, we'll do that here. You'll see that it ran through the loop and then it printed out I and it set up our Markdown. That's a pretty common method. If it runs into an error, it will pause execution. So that's important because sometimes in a lecture video, you might see we intentionally put an error in there for a teachable moment. Under the view, there's some options as well. Line numbers is one that I will often turn on, and that'll number our cells as well. Each Jupyter Notebook has a title for it, and this determines the file name. So I'll just call this demo. And if you click on the Jupyter logo, you'll be taken to what's called the tree interface, which is just a directory interface of the files that you have for this project. And within a given course on Coursera, or a specialization or a degree on Coursera, you may have any number of different Jupyter systems with different file spaces mounted on them. I also really like to be able to download my Jupyter notebooks. So sometimes I download them as HTML to show them to people, or as a PDF version. So that can be quite helpful as well. So that's a quick tour of the Jupyter Notebook. Now, most of the work you'll be doing in this course, this specialization or this degree, will be in the Jupyter Notebook. It's a great environment for doing Python, and there's ways to create assignments and to submit assignments directly to autograders from within the platform. And I hope that we'll be able to share some of our research tools as well on educational technology that are built into the Jupyter Notebook, but we'll see how that goes. All right, we'll see you in the course.
Hi everyone, my name is Daniel Shorin and I'm a student assistant in this class. Today we'll be going over how to set up your local programming environment on a Windows computer. We'll go through and install all of the libraries, packages, and software you'll need to run the files in this course. While the Jupyter console in the Coursera module comes included with all of the libraries and packages you'll need to run the lessons in this class, some people may prefer to do that on your own computer. The only prerequisites for this tutorial are a computer running Windows with administrative access that is connected to the internet. We'll be completing the installation using the command line, which is a way to pass instructions to your computer using text. The command line is also known as a shell and is a powerful tool for modifying, automating, and organizing tasks on your computer. Before we get too into the command line, let's first install Python. Navigate to this URL, https://www.python.org/downloads/windows, and download the latest version. At the time of this video recording, that's Python 3.73. This downloads an installer, which will automatically configure the paths and dependencies, allowing the programming language to be interpreted by your computer. Follow the instructions and you'll be good to go. Python automatically comes with a package called pip, which allows you to install libraries super easily. We'll touch more on pip in just a little bit. In order to download and manage libraries, we'll need to download a package manager. A package manager is a set of software tools that automate complex installation processes, which include downloading, upgrading, configuring, and removing software. The most robust and common package manager for Windows is Anaconda, which we'll be using in this guide. Anaconda is a free and open source package and environment management system that makes installing software on Windows pain-free. Additionally, Anaconda is a Python data science distribution, meaning it comes loaded with lots of useful libraries for data mining, machine learning, and statistics programming work. If you're interested in using these libraries, be sure to check out the University of Michigan's Applied Data Science and Python programming course on Coursera after this class. To download Anaconda, go into your web browser and navigate to www.anaconda.com/distribution and download the package manager corresponding to the Python version you downloaded. This will launch another installer program similar to the one you used for the Python installation. Follow the instructions, download it to the default location, and you'll be ready to go. If you already have Anaconda installed on your computer, you can update it to the latest version by typing conda update conda in your command line interface. Now that we have our package manager installed, let's talk about virtual environments. Virtual environments allow developers to have separate space for programming projects, ensuring that the dependencies of one project don't inadvertently affect another project's. Using virtual environments can prevent a lot of compilation issues, as well as giving more control over our Python projects. It's a best practice to create a programming environment for each programming project, as you can create as many of them as you'd like. Let's go ahead and create a virtual environment for this class, Py3. To do this, we'll use Anaconda's built-in virtual environment capabilities using the command line. On Windows computers, we can use the command line application to access the command line interface, which can run scripts, download software, and more. You can find the command line by opening the Start menu and scrolling through your applications, or by using the search bar. Once you have your command line opened, let's create a home directory for the files in this class. For this tutorial, we'll place it in a folder on your desktop, although you can put it wherever you'd like. Type cd squiggle line. That'll just take you back to your home directory. And then type cd desktop. CD stands for change directory, That'll help us change the directories and folders as we navigate using the command line. So cd desktop helps us navigate to our desktop. And then we're going to make a folder using the command make directory or makedir, mkdir, and then the name of our home folder for this class. And for this, we'll use py3. Now that we've had that folder created, we'll go into that folder using the change directory command. Now that we're in our class directory, we'll create our virtual environment simply by typing this command, conda create -n py3env python equals 3.72 and conda, where py3env is the name of our virtual environment, and the Python version corresponds with the Python version you downloaded. You can check the Python version by typing python -- version. Here on this computer, we're using Python 3.5. So now that we've created our virtual environment, we can activate it using the following command, which is simply source activate py3env, where py3env is the name of our environment. As you can see, the Windows built-in command prompt is having a hard time working with Anaconda. To work around this, we're going to use a command line interface program called git bash. Git bash is a shell which works on top of the command prompt to make it easier to download libraries and easier to work with your command line as a whole. To download git bash, just Google search git bash. Click on the downloads page. Click on your Windows operating system, and your download will start immediately. Follow the instructions on that download, and you'll be all set to use git bash. We'll go to our main directory, go to our desktop, go to our py3 folder. And now, since we already created the environment using the command line interface from the Windows computer, we'll go ahead and see if that's working with git bash. So we'll try source activate py3env. And wonderful, we're in our Python 3 virtual environment. You can tell that you are in your Python 3 environment if the name of your environment is in parentheses after any command. Now that we've created and activated our virtual environment, let's install the packages we'll need for this course. We'll describe more about what these packages do and how to use them in different lessons. For now, run the following commands, one at a time, in your py3 folder with your virtual environment activated. Due to the power of editing, we're going to speed through the process of copying and pasting these downloads into your git bash shell or your command prompt. And additionally, on this computer, these packages were already installed, so don't be alarmed if you see different instructions in your command prompt. We'll install pip install pillow, pip install py-tesseract, pip install numpy, pip install matplotlib, and pip install OpenCV Python. With all of your libraries downloaded, we're nearly ready to go. We just need to get our files ready to run. Let's navigate to the py3 Coursera class, download the Jupyter Notebook files with their IPYNB extensions and their accompanying data files into the py3 directory on your local computer. To run these files, we'll simply navigate to our folder in the command line and type Jupyter Notebook. And as you can see, our notebook is up here, all ready to go. If you install the files, they'll be ready for you to run. Thank you all so much, and have a ton of fun in this class. Hi everyone, my name is Daniel Shorin, and I'm a student assistant in this class. Today, we'll be going over how to set up your local programming environment on a Mac computer. Starting off, while the Jupyter console is included in Coursera, and it comes with all the included libraries and packages necessary to run the lessons in this class, some people may prefer to run the files on your local computer. Today, we'll go over the steps and help you do that in this video. The only prerequisites for this tutorial are a computer running Mac OS with administrative access that's connected to the internet. We'll be completing the installation using the command line, which is a way to pass instructions to your computer using text. The command line is also known as a shell, and it's a powerful tool for modifying, automating, and organizing tasks on your computer. On Mac computers, we use the terminal application to access the command line interface. You can find terminal by opening Finder and navigating to terminal in the utility folder within the applications folder. In order to download and manage libraries, we'll need to download a package manager. A package manager is a set of software tools that automate complex installation processes on your computer, which include downloading, upgrading, and configuring and removing software. The most robust and common package manager for Mac OS is Homebrew, which we'll be using in this guide. Homebrew is a free and open source package managing system that makes the installation process on Mac computers pain-free. To install Homebrew, copy the following command and paste it in the terminal as such. We'll go ahead and copy this link, navigate to our terminal, Control-click, paste, and enter. You'll see a script asking for permissions to download, and we'll go ahead and press return. And then you'll see it download and install Homebrew. So Homebrew is a software programmed in the language Ruby, and the installation works by modifying your computer's Ruby path, meaning where Ruby is installed on your computer. You'll need to confirm the download and enter your computer's password. Note that your keystrokes will not display in the terminal window when you're entering your password for security reasons, so simply press enter when finished typing your password and follow the instructions in terminal to finish the installation. Once that's finished, you can check if Homebrew installed successfully by typing the following command in your terminal. Just brew doctor. So we'll go ahead and copy that, go back and paste it, and we see that our system is ready to brew. Once Homebrew is finished installing, we can download Python. Homebrew comes included with a ton of packages available for easy installation. You can search for libraries to install using the brew search command. Feel free to browse Homebrew's packages on your own time. Now we can go ahead and install Python 3 using the following command in terminal. Brew install Python 3. So again, we'll go over, copy that, Control-click and paste it, and press enter. While Python 3 is already installed on this computer, you'll see a few different instructions in your computer's terminal. As you can see on our computer, it says we're already installed and up to date, but if you just follow the instructions in your terminal, your Python will install correctly. Upon entering that command, the terminal should be flooded with information about the download. In addition to Python 3, Homebrew will install pip, setup tools, and a wheel. These are all libraries and packages for Python. Pip assists Homebrew in Python package management. We'll be using pip momentarily to download the Python packages we'll be using in this module. We can check the version of Python we have using the following command, Python version. And as we see, we are working with Python 2.7.1. While this is an older version of Mac OS, we do recommend using Python 3 to download. To update the version of Python on your computer, we first recommend updating Homebrew. You can do so with the following commands. Brew update, and as we can see, Homebrew is already up to date on our computer. And finally, brew upgrade Python 3. Great. Now we can see that Python 3.7 is installed. Now that we have Homebrew and Python installed, let's talk about virtual environments. Virtual environments allow developers to have separate spaces for different programming projects, ensuring that the downloaded packages of one project don't inadvertently affect another project's. Using virtual environments can prevent a lot of compilation issues, and it can also give us more control over our Python projects. It's best practice to create a programming environment for each programming project, as you can create as many of them as you like. Let's go ahead and create a virtual environment for this class, Py3. First, we'll have to create a home directory to house the files in for this course. For this tutorial, we'll put it in a folder on our desktop, although for you, you can put it wherever you like. In terminal, type cd and the squiggle line. And that takes us to our home directory. Then we'll type in cd desktop. And then we type the command makedir, mkdir, and the name of your folder, which we'll use Py3. We'll navigate into this folder using the change directory or cd command. Now that we're in our class directory, we can create our virtual environment simply by typing this command. In this command, the 3.7 corresponds to the version of Python, and py3env is the name of our environment. This command creates a new directory inside of our py3 home folder that houses a few files that allow our virtual environment to run correctly, isolating the project files so that they don't mix with the system files on our computer. The most important of these is the lib subdirectory, which starts out empty but will, at the end of this lesson, hold the data for all the libraries we install in this environment. To use the environment we created, we need to activate it. We do this by invoking the activate script in terminal. Wonderful. And you know your virtual environment is activated when you see the name of your environment in parentheses before the terminal commands in the application. Now that we've created and activated our virtual environment, let's install the packages we'll need for the course. We'll describe more about what these packages do and how to use them in different lessons. For now, just run the following commands, one at a time, in your py3 folder with your virtual environment activated. Due to the power of editing, we're going to speed through this installation process, but understand that these packages may take some time to install, so be patient with them. Install pip install pillow, Tesseract, py-tesseract, NumPy, matplotlib, and OpenCV Python. With all of our libraries downloaded, we're nearly ready to go. We just need to get our files ready to run. Let's navigate to the Py3 Coursera course, download the Jupyter Notebook files with the IPYNB extensions and their accompanying data files, and put those into the Py3 directory on our own computer. To run these files, we simply navigate to our folder in terminal and type Jupyter Notebook. There you should see a folder for your files, and you'll be all ready to go and run these files within Jupyter. Thank you so much, and have fun with this course.
So let's demystify the Python runtime environment a bit. Up until now, you've been learning how the code itself works. That is, how the Python interpreter, which is a computational process running on your computer, considers the commands you give it, which are loops, control structures, variables, functions, and how it executes the underlying code on hardware, such as the processor, video card, and memory of your computer, to create some experience for the user. In much of this course, you've been using a web-based simulation environment, Runestone, to create these experiences. With Jupyter, though, we'll be using an environment that is more traditional. A key aspect of this traditional environment are the installation files for Python itself. Let's take a look. I'm going to open up a new terminal. Don't worry if this seems unfamiliar to you. We won't be using the terminal much in this course. I just want to help you explore the Jupyter system a bit. You'll notice that there are a bunch of characters when we open up the terminal. The first set of characters are our username. You can ignore this. It should be the same, Jovian, for all Coursera users. Then there's an @sign, and the next set of characters are the machine name. Again, the machine name is just auto-generated by the Coursera system and isn't really relevant for our discussion right now. Finally, the rest of the string is the current path, or the location that we're working in. This is useful, and actually if we type the characters L and S in there for list and hit enter, we'll see a list of all files and subfolders in this directory. But I actually want to show you where Python lives on this machine. So we're going to change the directory with the command cd. On the Coursera system, we're using a specific kind of installation for Python called Anaconda. Don't worry too much about that. Let's just change to the site packages directory. This is the real heart of the Python library ecosystem. So I'll go cd, optconda, lib, python 3.6, and site packages. When we do this, then do a directory listing, we see a whole bunch of things. First, There's a lot of interesting files and directories in here, and these are the third-party packages for Python which are installed on the system. We're going to be dealing with a lot of new packages, but I want you to feel empowered to explore a bit. These packages are just Python files, or sometimes other languages as well, which have been configured to work with the current Python environment. Let's take a look at one that I'm familiar with, called Pillow. Pillow is an imaging library for Python. We can see that it's installed here because there's a Pillow egg file. We can actually look at the source code of the Pillow library by going into the pill directory. So let's cd pill. You'll see that when we do an ls, most of these files are just .py files, Python code itself. We can even take a look at the Python source code behind this library using the more command. Here, let's look at the main Python file in this library called image.py, so more image.py. We can see that there's a bunch of comments at the top, reaching all the way back to 1995. We see a few import statements, then some top-level variables like a logger. We won't talk much about loggers, but they're handy when debugging code. Then we see that there are a few classes which are created, then a math expression, then a try and except block, and so forth. You can feel free to explore this library more by hitting the space bar, or you can exit with the more command by hitting Q. So that's a very brief overview of where Python libraries exist on your system. Now, that's not exactly a user-friendly way to interact with the library by reading the source code, but it's a great way to learn how libraries work and how programmers create complex Python solutions. But let's go back into the Jupyter Notebook and explore how to actually use this library. You'll recall that we import a library using the import keyword. So just import pill and we run this. Documentation is a big help in learning a library. There exist standards that make this process easier. For example, most of the libraries let you check their version using the version attribute. So we go pill dot and then a double underscore, so this is called dunder version dunder. And we see the version of the one that I'm using is 4.2.1. You might be using a different version because we might have upgraded it. Let's figure out how to open an image with Pillow. Python provides some built-in functions to help us understand the functions and objects which are available in libraries. For instance, the help function, when called on any object, returns the object's built-in documentation. Let's try it with our new library module, pill. So help pill, and this renders nicely in line a bit of help file that actually comes from the documentation of the source code itself. This shows us that there's a host of classes available to us in the module, as well as version information, and even the file called dunder.init.dunder.py, which has the source code for the module itself. We could look up the source code for this in the Jupyter console if we wanted to. These documentation standards make it easy to poke around and explore a library. Python also has a function called dir, which will list the contents of an object. This is especially useful with modules where you might want to see which classes you might interact with. Let's list the details of the pill module. So dir pill, and we can see here a list comes back with a bunch of strings. Most of these are intended to be internal functions, so they've got dunder before and dunder after, and that's just double underscore. That's a fancy way in Python that they say. And we see that there's a couple that do not have dunder and are expected to be used more generally. At the top of this list, there's something called image, and this sounds like it could be interesting for us. So let's import it directly and run the help command on it. So from pill, we'll import image, then help image. Running help on the image tells us that this object is the image class wrapper. We see from the top-level documentation about the image object that there's hardly ever any reason to call the image constructor directly. and they suggest that we use the open function, and that's what we should be using to get images. Let's call help on the open function to see what it's all about. Remember that since we want to pass in the function reference and not run the function itself, we don't put parentheses behind the function name. So help image.open. And we're passing an object, but that object is actually a reference to the function. So it looks like image.open is a function that loads an image from a file and returns an instance of the image class. Let's give it a try. In the read-only directory, there's an image I've provided, which is from our Masters of Information program recruitment flyer. Let's try and load that now. So file, we'll make it a string, read-only directory, and then msi_recruitment.gif. And we'll call image.open and pass it this path to the file, and that should return to us an image object, which we're going to put into the image variable. And let's just print out this image. Okay, so we see it printed a pil.gifimage plugin.gif file, and it gives us some other information there. So we see that this returns to us a kind of pil.gifimage plugin.gif file. At first, this might seem a bit confusing because we were told by the docs that we should be expecting a pil.image object back. But this is actually just object inheritance working. In fact, the object returned is both an image and a GIF image file. We can use the Python inspect module to see this, as the getMRO function will return a list of all of the classes that are being inherited by a given object. Let's give it a try. So we'll import inspect. Now this is not a third-party library, it comes with Python. And then we'll write a function, we'll just print the type of the image, and so type will tell us all of the types of the image, type will tell us the type of the image, but we want to convert that to a string. But then we're going to call inspect.getMRO and pass it the type of the image and see what that inheritance chain looks like. So we see the result is a tuple that's returned to us, which is actually all of the different objects that are being inherited from here. With GIF image plugin at the very, usually bottom we would call this of the inheritance, the most specific version, up to an image file, up to an image, and then up finally to an object. Now that we're comfortable with the object, how do we view the image? It turns out that the image object has a show function. You could find this by looking at the properties of the object if you wanted to, using the dir function. So we'll call image.show, and that didn't seem to have the intended effect. The problem is the image is stored remotely on Coursera's server, but show tries to show it locally to you. So if the Coursera server software was running on someone's workstation in Mountain View, California, where Coursera has its offices, then you just popped up a picture of our recruitment materials. Thanks for that. Instead, though, we want to render the image in the Jupyter notebook. And it turns out Jupyter has a function which can help with this. So from ipython.display, and we'll talk a little bit more about that, but IPython was one of the early terms for Jupyter. It started as just an interactive Python interpreter before moving into a much larger project. We want to import the display function, and then let's call display and pass it the image. Okay, so there we see our inline display of happy Masters of Science and Information students. For those who would like to understand this in more detail, the Jupyter environment is running a special wrapper across the Python interpreter called IPython. IPython allows the kernel backend to communicate with the browser front end, among other things. The IPython package has a display function which can take objects and use custom formatters in order to render them to the screen. There's a lot of different formatters provided, including ones which know how to handle image types and different image types, and that's what we're using here. That's a quick overview of how to read and display images using Pillow. In the next lecture, we're going to jump in a bit more into detail to understand how to use Pillow to manipulate images. First, let's import the PIL library in the image object. So import PIL, and then from PIL we'll import image. And let's import the display functionality from IPython. So from ipython.display, we'll import display. And finally, let's load the image we were working with last time. So that image is in read-only msi-recruitment.gif. And now we'll open it into the image object. Let's execute that cell. Great. Now let's check out a few more methods of the image library. First, we're going to look at copy. And if you remember, we can do this using the built-in Python help command. So help image.copy. All right, so here's some information about copy. We see that the copy takes no arguments and that the return object is an image object itself. Now let's look at save. So help image.save. Okay, so there's quite a bit to the image.save object. The image save method has a couple of parameters which are interesting. The first, called fp, is the file name we want to save the object to. The second, format, is interesting. It allows us to change the type of the image, but the docs tell us that this should be done automatically by looking at the file extension as well. Let's give it a try. This file was originally a GIF image file, but I bet if we save it with a .ping format and read it in again, we'll get a different kind of file. So let's image.save, and we'll just call it msi-recruitment.ping, and that's going to save it in your home directory. And then we'll open a new image, so image.open msi-recruitment.ping, and take that into an image variable. Now let's import inspect like we did in the previous lecture, and call inspect.getMRO and wrap an image in the type function. Indeed, this created a new file, which we could view by going into the Jupyter Notebook file list by clicking on the logo at the top of the browser. And we can see this new object is actually a ping image file object. For the purposes of this class, the difference between image formats really isn't so important, but it's nice that you can explore how a library works using the functions of help, dir, and getMRO. The Pillow library also has some nice image filters to add some effects. It does this through the filter function. The filter function takes a filter object, and those are all stored in the image filter object. Let's take a look. So from pill, we'll import the image filter object, and then run help on image filter. So there are a bunch of different filters here, but let's just try and apply the blur filter. Before we do this, we have to convert the image to what's called RGB mode. This is a bit magical. Images like GIFs are limited into how many colors can be displayed at once, based on the size of the palette. This is similar to a painter's palette, which only has so much room. This is actually a very old image format. If we convert the image into something more sophisticated, we can apply these interesting image transforms. Sometimes learning a new library means digging a bit deeper into the domain the library is about. We can convert this image using the convert function. So we'll image, and then we'll just call image.convert RGB, and this stands for red, green, and blue mode, which is a pretty common mode for images. Then we'll create a new variable, blurred image, and we'll set that to image.filter, and we'll pass in the pill.imagefilter.blur parameter. You'll note that the parameter that we're passing in is really a placeholder. It's not a function that we're running, it's an object we're passing in. And then let's display that blurred image. I encourage you to pause the video here and jump into the notebooks and start experimenting with some of the other filters. The emboss and sharpen filters, for instance, are interesting. Or for a challenge, check out the box blur or the median filter functions and look at their parameters to get a sense of how they're being used. Okay, let me show you one more function in this lecture, which is crop. This removes portions of the image, except for the bounding box that you describe. When you think of images, think of individual dots or pixels which make up the image being lined up on a grid. You can actually see the number of pixels high the image is and the width of the image. So let's do that here. We'll print the image. We'll use the string formatting to pass in two parameters. The first is going to be image.width, the width of the image in pixels, and image.height, the height of the image in pixels. We see it's 800 by 450. This means that this image is 800 pixels wide, and we call that the x-axis, and 450 pixels high, and we call that the y-axis. If we take a look at the crop documentation, we see that the first parameter to the function is a tuple, which is the left, upper, right, and lower values of the x-y coordinates, so the two corners of the image. So help image.crop, and we run that, and we see that there's a box that we provide. With PIL images, we define the bounding box using the upper left corner and lower right corner. And we count the number of pixels out from the upper left corner, which is 0, 0. This might seem odd if you're used to coordinate systems which start in the lower left. A lot of us learned these in primary school mathematics. Just remember that we define our box in the same way we count out the positions in the image. So, if we wanted to get the Michigan logo out of this image, we might start with the left at, say, 50 pixels, and the top at 0 pixels. And then we might walk to the right another 190 pixels and set the lower bound to, say, 150 pixels. So let's display, and we'll call image.crop, and we pass it, a parameter is a tuple. So remember that we're going to put all 4 of these parameters in one tuple object and pass it in, and this should display the image. And there we go. That's the School of Information logo cropped out of the image. Of course, crop, like other functions, only returns a copy of the image and doesn't change the image itself. A strategy I like to do is to try and draw the bounding box directly on the image, where I'm trying to line things up. We could draw on images using the image draw object. I'm not going to go into this in detail, but here's a quick example of how I might draw the bounding box in this particular case. So from PIL, we'll import the image draw object. We'll instantiate this, so we'll call imageDraw.draw, and we pass it the image, and you can check the documentation to learn more about how you would use this object. Then we say drawingObject.rectangle, and we give it the rectangle, the outline that we're actually interested in, and we give it a fill value, and you can set the fill to different colors or types, and then an outline, and in this case we want to make it red. And because we ran this on the drawing object, it actually executes it, and the drawing object has a reference to the underlying image. So let's display this image now in the Jupyter Notebook. And there we go. We have an image, which is our main image of the logo that's outlined in the red box for our flyer. Okay. That's been an overview of how to use PIL for single images. But a lot of work might involve multiple images. And in fact, your assignment involves multiple images. So in the next lecture, we're going to tackle that and set you up for this assignment. I'll see you there. Let's take a look at some other functions we might want to use in Pillow to modify images. First, let's import all of the library functions we need. So we'll import PIL like we've been using. From PIL, we'll import image. And from ipython.display, we'll import display. And let's load the image we're working with. And we could just convert it to RGB inline. So that image was in read-only/MSI recruitment.gif. And here we'll just image.open the file, and then that returns an image object, which we call convertOn, send it the RGB string, and now we've got our image. Let's just display that image in line here. All right, so that's the image we've been working with. A task that's fairly common in image and picture manipulation is to create contact sheets of images. A contact sheet is one image that actually contains several other different images. So let's try and make a contact sheet for the Master of Science and Information advertisement image. In particular, let's change the brightness of the image in 10 different ways, then scale the images down to smaller sizes and put them side by side so that we can get a sense of which brightness we might want to use. So first up, let's import the image enhance module, which has a nice object called brightness. So from PIL, import image enhance. Checking the online documentation for this function, it takes a value between 0.0, which is a completely black image, and 1.0, which is the original image, to adjust the brightness. All of the classes in the Image Enhance module do this in the same way. You create an object, in this case brightness, then you call the enhance function on that object with the appropriate parameter. Let's write a little loop to generate 10 images of different brightnesses. First, we need the brightness object with our image. So we'll create a variable called enhancer, and we'll set this to imageenhance.brightness and pass in the image. Now let's create a new list for our images. And then for each image, so from 0 to 10, let's do some processing of this. So we'll divide I here by 10 to get the decimal values we want and append it to the images list. We actually call the brightness routine by calling the enhance function, as I said. So remember that you can dig into the details of this using the help function if you want to, or by consulting the web docs. So we'll do images.append, and we'll do enhancer.enhance, and we'll just take our counter parameter here, I, and divide it by 10. Well, first we'll get 0, and then 0.1, 0.2, and so forth. We can see that the result here is going to be a list of 10 pill image.image objects. Jupyter nicely prints out the value of Python objects nested in lists. So let's just print out the images here. And there we go. We can see that we have these pill.image.image objects, and pill actually, when we call print on them, the repr function has been written, so we get to see a little bit more information about each of these objects. We see that the mode is RGB, of course we knew that because we converted that, but we also see the size, and then they give us a memory location, which for our cases is not particularly interesting, but you can see that that changes for each of the images, so we know they're pointing to different images. Let's take these images now and composite them, one above another, into a contact sheet. There are several different approaches we can use, but I'll simply use a new image, which is like the first image, but 10 times as high. Let's check out the pill.image.new functionality. So we can do this using help. We just say help pill.image.new and run that cell. The new function requires that we pass to it a mode. We're going to use the mode RGB, which stands for red, green, blue, and it's the mode of our current first image. There's lots of different image mode formats, and this one is actually one of the most common. For the size, we have a tuple, which is the width of the image and the height. We'll use the width of our current first image, but for the height, we'll multiply this by 10. This will make a sort of canvas for our contact sheet. Finally, the color is optional, and we'll just leave it to black. So we'll create a new variable here called first image, and we'll use that a lot. And it's just the first image from the list, but we're going to use it as a reference for sizes. From pill, we want to import image. And then let's create the contact sheet. And so this is, we call pill.image.new, so we're invoking the image new constructor, or what will be a constructor, to give us the first image mode. So that's RGB, that's the first parameter. And then we give it the width, and then 10 times the height. So now we have a black image that's 10 times the size of the other images in the contact sheet variable. Now let's just loop through the image list and paste the results in. The paste function will be called on the contact sheet object, and it takes in a new image to paste, as well as an XY offset for that image. In our case, the X position is always 0, but the Y location will change by 450 pixels each time that we iterate through the loop. So let's first create a counter variable for the Y location. It will start at 0. So we'll call that counter current location. And then for each image in our images list, let's paste the current image into the contact sheet. So we call contact sheet.paste, we give it the image, and we give it a 0, which is the X location, so to the far left, and then the current location, which is our Y location. And then let's update the current location counter. So we update this by increasing it by 450 pixels, which is the height of our image. This contact sheet has gotten big, 4,500 pixels tall. Let's just resize this sheet for display. We could do this using the resize function. This function takes in a tuple of width and height, and will resize everything down to the size of just 2 individual images. So we just call contact sheet.resize and give it the tuple size that we want it to scale to. Now let's just display that composite image. So we'll call display with contact sheet. You can see here that we have all of these images. They're stacked upon one another, and they're different brightnesses. They really go from quite dark, maybe even black, to almost our full normal image. Okay, so that's a nice proof of concept, but it's a little tough to see. Let's instead change this to a 3x3 grid of values. And this is something you'll use in your assignment. So first thing we should do is make our canvas. We'll make it 3 times the width of our image and 3 times the height of the image, a 9-image square. So we'll call pill.image.new. Again, we want to pass in the mode of the image we're using, and then the width and the height each multiplied by 9. And we'll save this as our new contact sheet. Now, we want to iterate over our images and place them into this grid. Remember that in pill, we manage the location of where we refer to an image in the upper right-hand corner. So this will be 0.0. Let's use one variable for the x dimension and one for the y dimension. So x equals 0 and y equals 0. Now, let's just iterate over our images. Except we don't want to bother with the first one because it's just solid black. Instead, we want to just deal with the images after the first one. And that should give us a 9 total. So for image in images, and we just use slicing here to pull out from the first image, that is the one in the 1 position as opposed to the 0th position, to the end of the list. And that gives us a sublist that we're going to iterate over. Let's paste the current image into the contact sheet. And so we do this with contact sheet.paste, and we pass in the image and the XY position. Now we need to update our X position. If it's going to be the width of the image, then we set it to 0, and we update Y as well to the point to the next line of the contact sheet. So if X plus first image.width is equal to the contact sheet.width, we'll set X to 0, and we'll update Y, and we'll make Y equal to the first image.height. So if this isn't true, then we'll just update X. And so X will be equal to X plus the first image.width. And this will move us over a little bit horizontally, but won't change our vertical alignment. Now, let's resize the contact sheet. We'll make it just half the size by dividing it by 2. And because the resize function needs to take round numbers, we'll need to convert our divisions from floating point numbers into integers using the int function. And so we'll take our contact sheet, we'll resize it, and we want to really pass 2 parameters, but we need to wrap those in int calls to make them integers, whole numbers, because we're doing a division. And so when you take 2 integers and divide one by the other integer, you always get a floating point return, and we want to typecast this into integers. Now let's display that as a composite image. And so just like before, we display the contact sheet in Jupyter. And we see here we have our 3x3 grid. In the upper left, we start with very dark, and it gets lighter as we go across, and then it wraps around, and it gets lighter and lighter until we get to the lightest image in our brightness levels at the lower right. And you could see actually how a photographer who might be looking to change the brightness of an image, let's say they're going to put it in the background of a video, or they want to put it as a background of a page and put text over it, might want to see it in a bunch of different variations, a bunch of different brightnesses, and we've written a function which could do that. So if something like Photoshop was written in Python, you could wire up a button now with this logic that just shows a bunch of alternative versions of the image. Well, that's been a tour of our first external API, the Python Imaging Library, or the Pillow module. In this series of lectures, you've learned how to read and write images, manipulate them with Pillow, and explore the functionality of third-party APIs using features of Python like dir, help, and getMRO. You've also been introduced to the console and how Python stores the libraries on the computer. While for this course, all of the libraries are intended for you to use in the Coursera website in the Jupyter system, and you won't need to install your own, it's good to get the idea of how this work is done in case you wanted to set things up on your own PC. Finally, while you can explore Pillow from within Python, most good modules also put their documentation up online, and you can read more about Pillow here at Read the Docs. And this will be very useful for your assignment, which comes up soon. All right, now it's time for the assignment. So the first assignment actually follows on the first set of lectures and uses PIL and the Pillow library. And so I've done a bunch of digital photography just as a hobby myself. And something I'm very interested in is creating variations on images. So I'll take a nice photo, and I did some black and white photography, and I wanted to see that photo in sepia tones, so little browns or warm colors, or I wanted to see it in cool gray tones. It gives it a more architectural feel, a more distant, and it changes the emotion. Even though it's a black and white image, usually there's not just black and white. And this is interesting both in the images that we can create digitally, but actually there's this whole world of pigmentation and color science as well when it comes to actually printing these kinds of images. So in this assignment, I want you to improve upon variations that we did in the main lecture. So we looked at variations of brightness, but I'm going to let you dig a little bit further into this RGB setup of images. So in an image, a given pixel, a 1 by 1 pixel, can be represented as red, green, and blue color channels. And those three things are mixed together to provide an overall color. So purple might have a lot of red and a lot of blue in it, and a little bit of green, for instance. And so in this assignment, you're actually going to manipulate those color channels directly and create a contact sheet that shows us what some of those manipulations look like. So have some fun with this assignment. I think you can explore quite a bit about image and images in this assignment. If you do any digital photography, if you do stuff with Photoshop or the like, you'll probably enjoy this assignment. And I'll see you next week when we talk about Tesseract and optical character recognition. Optical character recognition, or OCR, is the conversion of text captured in images into text usable by a computer. In other words, an OCR tool can read the text in images. OCR is a common method of processing large volumes of printed text, especially when that text isn't available in a digital format. In practical application, OCR has been used to scan the pages of books, to recognize license plates, and even to convert handwriting into digitized text. Let me share an example from my own work. During my doctoral degree, I was working on an open source system called OpenCast Matterhorn. This system allows for the automated recording of lectures within universities, similar in some ways to the video you're watching now. The system generally ran automatically when an instructor was teaching a course, and the video was uploaded to the web immediately following the lecture without any input from technicians. This was great, but it was hard to find videos about a given topic that might have been covered during the lecture. To deal with this, we built a search index from the contents of videos themselves. We essentially broke a video up into a sequence of images, ran OCR on each image to determine what text might have been shown to the students from the slides in the classroom, then created a search index using this technique. In the project for this course, you're going to be doing something similar, but we're going to do it with images of newspapers instead. In this module of the course, we're going to use an OCR engine called Tesseract. Tesseract was originally developed between 1984 and 1994 as a PhD research project at HP Labs. The engine vastly outperformed commercial products at the time, but then development was stopped until HP released Tesseract as open source in 2005. In 2006, Google began maintaining the tool and has since released updated versions of Tesseract with support for over 100 languages. I think Tesseract is a great tool and a wonderful example of how companies can engage in open source software development. So before we spend a lot of time talking about Tesseract, let's talk more about open source software. Have you noticed that the source code for all of the libraries we've discussed is openly available to the public? Publicly available software is often known as open source software, or OSS. Specifically, open source software is software whose creator released the source code under an open source license, thereby granting anyone the right to access, modify, and distribute the software. The Open Source Initiative, OSI, defines open source software as software that can be freely accessed, used, changed, and shared in modified or unmodified form by anyone. You can find the full criteria for open source software on the OSI website. The first three stipulations are the core of OSS. That is, that the software is available without charge, the source code is public and accessible, and that this license, whatever it is to be adhered to by all derivative works. Open source development was pioneered by computer scientist Eric Raymond in his landmark 1997 essay, The Cathedral and the Bazaar. It is well regarded as a software development technique as it lowers consumer cost and increases code flexibility, security, and accountability due to its community-sourced nature. And there's good business sense to using open source software too. According to a 2008 study, OSS saves consumers $60 billion annually, and much open source software allows companies to build on top of it, lowering infrastructure costs. There are different types of open source licenses, and the field can be a bit confusing to understand, especially for businesses. For example, the Apache license allows the linking of Apache licensed code with differently licensed code. As a developer, you may find such a license feature useful if you want to include a closed source library or a proprietary library in your open source project. On the other hand, under the GNU Public License, or GPL, one can link only other GPL-compatible libraries. You may find this license feature desirable if your open source project is composed of entirely open source code, and you wish to ensure that this will always be the case, regardless of who in the future uses your code. The GPL is probably the most well-known and perhaps common open source software license, in part due to its viral nature, which requires all linked software to also be GPL licensed. One of my favorite licenses to use, and a license I love to see used on libraries that I use, is called the BSD license. It was originally put together by the University of California, Berkeley for the release of the BSD operating system. Here's an example of the BSD license. As we can see, it's very short and to the point. It maintains just a minimal amount of legalese. The issues surrounding the features of free and open source licenses quickly become political and philosophical, and the choice of license often depends on the project that you have in mind. If you're interested in understanding open source licenses in more detail, I would encourage you to check out the Wikipedia article on the topic, and we'll have that linked in the course. For the rest of the lectures in this module, we're going to use two projects: the Tesseract project, which is now run by Google, and the py-tesseract bindings, which allows us to use the Tesseract system from within Python. If we look at the source code repository for Tesseract, we see that its license is released under the Apache license. This means we can use Tesseract in any of the code we produce and keep it licensed however we want, even commercially licensed, for instance, unless we change Tesseract itself. However, when we look at the py-tesseract license, we see it is released under the GPL. That means by importing this library into our own code, if we share it with others, we must also license our code under the GPL. This is the viral clause, and depending on the project I were working on, I would have to consider this very carefully. However, for this course, it's no problem, since I really do want to share it with you and others broadly. So let's dig in and let's start using Tesseract. We're going to start experimenting with Tesseract using just a simple image of nice clean text. Let's first import pil from image and display the image text.ping. So from pil we'll import image. Then image is equal to image.open, and we'll get the text.ping out of the read-only, and then we'll display that image. Great. We have a base image of some big clear text. Let's import py-tesseract and use the dir function to get a sense of what might be some interesting functions to play with. So import py-tesseract, then we can use dir to see what's inside of it. Okay, it looks like there's just a handful of interesting functions, and I think image to string is probably our best bet. Let's use the help function to interrogate this a bit more. So help py-tesseract image to string. So this function takes an image as the first parameter, and there's a bunch of optional parameters, and it'll return the results of the OCR. I think it's worth comparing this documentation string with the documentation we were receiving from the pillow module. Let's run the help command on the image resize function. So help image, image.resize. Notice how the pillow function has a bit more information in it. First off, it's using a specific format called restructured text, which is similar in intent to document markups such as HTML, the language of the web. The intent is to embed semantics in the documentation itself. For instance, in the resize function, we see the words param size with colons surrounding it. This allows documentation engines, which create docs from the source code, to link the parameter to the extended docs about that parameter. In this case, the extended docs tell us that the size should be passed as a tuple of width and height. Notice how the docs for image to string, for instance, indicate that there's a lang parameter which we could use, but then fail to say anything about what that parameter is for or what its format is. What this really means is that you need to dig deeper. Here's a quick hack if you want to look at the source code of a function. You can use the inspect get source command and print the results. So let's import inspect, and remember this module comes from our Python 3 standard library. And then we'll create the source, inspect.getSource, and we pass it a function pointer. You note that we're not calling the function, we're just passing a reference to the function, and then let's print that source to the screen. So it's kind of interesting. You can actually look at the source code behind a given function, and that's one of the powers of an interpreted language like Python. There's actually another way in Jupyter, and that's to append 2 question marks to the end of a given function or module. Other editors have similar features, and this is actually a great reason that you should be using a software development environment. So py-tesseract.image to string, just as if we were going to call the function, add 2 question marks to the end and then run that. And we see that that it pops up at the bottom of the screen with a lot more information, and it's nice and syntax highlighted for us too. We can see from the source code that there really isn't much more information about what the parameters are for or what this image to string function is. This is because underneath, the py-tesseract library is calling a C++ library which does all of the hard work, and the author just passes through all of the calls to the underlying Tesseract executable. This is a common issue when working with Python libraries, and it means that we need to do some web sleuthing in order to understand how we can interact with Tesseract. In a case like this, I just Googled Tesseract command line parameters, and the first hit was what I was looking for. Here's the URL to the GitHub. This goes to a wiki page which describes how to call the Tesseract executable. And as we read down, we see that we can actually have Tesseract use multiple languages in its detection, such as English and Hindi, by passing them in as eng plus hin. That's very cool. One last thing to mention. The image to string function takes in an image, but the docs don't really describe what this image is underneath. Is it a string to an image file, a pillow image, or something else? Again, we have to sleuth and/or experiment to understand what we should do. If we look at the source code for the py-tesseract library, we see there's a function called run and get output. Here's a link to that function on the author's GitHub account. And when we look at this function, we can actually see what actually happens when we call this function. In this function, we see that one of the first things which happens is the image is saved through the save image function. Here's that line of code. And we see that there's another function called prepare image, which actually loads the image as a pillow image file. So yes, sending a pill image file is appropriate for use for this function. It sure would have been useful for the author to have included this information in restructured text to help us not have to dig through the implementation itself. But this is an open source project. Maybe you would like to contribute back some better documentation? And just a hint, if you're interested in it, the doc line we need is param image, and then we just say that it's a pill image.image file or an ND array of bytes. In the end, we often don't do this full level of investigation, and we just experiment and try things. It seems pretty likely that a pill image.image would work, given how well known pill is in the Python world. But still, as you explore and use different libraries, you'll see a breadth of different documentation norms, so it's useful to know how to explore the source code. And now that you're at the end of this course, you've got the skills to do so. Okay, let's try and run Tesseract on this image. So text is equal to py-tesseract.image to string, and we pass in the image, and then let's just print out the text. Looks great. We can see that the output includes new line characters and faithfully represents the text, but doesn't include any special formatting. Let's go on and look at something with a bit more nuance to it next. In the previous example, we were using a clear, unambiguous image for conversion. Sometimes there will be noise in images you want to OCR, making it difficult to extract the text. Luckily, there are techniques we can use to increase the efficacy of OCR with py-tesseract and Pillow. Let's use a different image this time, with the same text as before but with added noise to the picture. We could view this image using the following code. So from pill, we'll import image, pretty common for us now. Then we'll do an image.open and we'll pull out this noisy ocr.ping, and then we'll use the display function in Jupyter to display it inline. As you can see, this image has shapes of different opacities behind the text, which can confuse the Tesseract image. Let's see if OCR will work on this noisy image. So import py-tesseract. Then we'll call py-tesseract.image to string, and we'll just pass it in the image that we're going to open this noisy OCR, and then let's print out the text directly. This is a bit surprising given how nicely Tesseract worked previously. Let's experiment on the image using techniques that will allow for more effective image analysis. First up, let's change the size of the image. So first we import pill. Then we set the base width of our image. So the base width, we'll set it to 600 points. These are in pixels. Now let's open the image. So that's old hat for us now, and we'll assign this to IMG. We want to get the correct aspect ratio, so we can do this by taking the base width and dividing it by the actual width of the image. So I'm going to create a new variable called w% and make this equal to the base width divided by the image.size sub 0, which is the width value there. With the ratio, we can just get the appropriate height of the image too. So I'll make something called h-size and set this to image size sub 1, and we'll times that by the percentage. So we're just scaling here. Finally, let's resize the image. Anti-aliasing is a specific way of resizing lines to try and make them appear smooth. So here I'll just call image.resize. I pass it a tuple, which is the base width and the height size, and then I use this pill.image.antialias to really just create better lines. Now let's save this to a file. So I'll call this image.save resize noise.ping. You could call it whatever you'd like. And finally, let's display it inline. So we'll call display, and then let's run OCR. So again, py-tesseract image to string, and I'm going to open this new image underneath. I guess I could have just passed in the image here, and then print the text. So there's not actually any improvement for resizing the image, and this is sometimes life when you're experimenting and trying to get things like this to work. Let's convert the image to grayscale. Converting images can be done in many different ways. If we poke around in the Pillow documentation, we find that one of the easiest ways to do this is with the convert function, and we pass in the string a capital L. So let's open the image that we're working with, and then let's call img.convert and pass in a capital L. Now let's save that image. I'm going to call it grayscale_noise.jpg here. Remember, PIL always worries about the file format for you based on the name of the image. So ending in .jpg here versus ending in .ping is fine. And then let's run OCR on the grayscale image. And so to prove there's no shenanigans, I'll open that grayscale image that we saved and pass it to image to string in py-tesseract and print out the text. Wow, that worked really well. So if we look at the help documentation using the help function, as in help img.convert, we see that the conversion mechanism used is the ITU-R601-2 Luma transform. There's more information about this out there, but this method essentially takes a 3-channel image where there's information for the amount of red, green, and blue, or RG and B, and reduces it to a single channel to represent luminosity, and that's what the L is for. This method actually comes from how standard definition television sets encode color onto black and white images. If you get really interested in image manipulation and recognition, learning about color spaces and how we represent color, both computationally and through human perception, is a really interesting field. Even though we now have the complete text of the image, there's a few other techniques we could use to help improve OCR detection in the event that the above two don't help. The next approach I would use is one called binarization, which means to separate into 2 distinct parts, in this case black and white. Binarization is enacted through a process called thresholding. If a pixel value is greater than a threshold value, it'll be converted to a black pixel. If it is lower than a threshold value, it'll be converted to a white pixel. This process eliminates noise in the OCR process, allowing greater image recognition accuracy. With Pillow, this process is straightforward. So let's open the noisy image and convert it using binarization. So here we just image.open, we're going to read our noisy image in, and then we call convert and we pass in the character 1. Note that we're passing it in as a character, not as a number, so this is a string value we're passing in. Now let's save and display that image. So img.save, we'll call it black and white noise.jpg and display it. You can see here the image looks kind of dotted and mottled. There's various different patterns in it, but definitely this is a black and white image. So that was a bit magical, and it really required a fine reading of the docs to figure out that the number 1 is the special string parameter to the convert function that actually does the binarization. But you actually have all the skills you need to write this function by yourself. Let's walk through an example. First, let's define a function called binarize, which takes in an image and a threshold value. So I'll def binarize and image to the transform and then some threshold value. Now let's convert the image to a single grayscale image using convert. So here we just create some new output image. This is what we'll end up returning, and we'll transform the image that's passed in by the caller to luminosity values only. So right now there's nothing new magical here to be done. This is just creating a grayscale image. The threshold value is usually provided as a number between 0 and 255, which is the number of bits in a byte. The algorithm for the binarization is pretty simple. Go through every pixel in the image, and if it's greater than the threshold, turn it all the way up, so to 255, and if it's lower than the threshold, turn it all the way down, so that's to 0. So let's write this in code. First, we need to iterate over all the pixels in the image. So for x in range, and we'll just go over the width, so values along the x-axis, and then for y in range, and we'll go through the height, so these will be our values through the y-axis. So for a given pixel at some width and height, let's check its value against the threshold. So we can do this with if output image.getPixel, we'll just pull the pixel x and y. You'll note lots of brackets here. That's because we are actually passing a tuple value in. We just check to see if it's less than some threshold value. So let's set this to 0 if it is. So in our output image, we just put that pixel, and we pass in the same xy, and we put it to 0. So we're just changing it to 0 if it's less than a threshold. Otherwise, we want to set this to 255. So output image.put pixel xy 255. And now we just return the new image. So let's test this function over a range of different thresholds. Remember that you can use the range function to generate a list of numbers at different step sizes. Range is called with a start, a stop, and a step size. So let's try the range 0, 257, and 64, which should generate 5 images of different threshold values. So for thresh and range 0 to 257, and then we're going to step at 65. Let's print out a string to tell us what threshold we're trying here. And so we want to change, remember, the thresh value is an integer, so we'll change it to a string here using the str function. And then let's display the binarized image in line. And so the way we do this is the display function, then we're going to call our function binarize, and we're going to pass it the image.open, read-only, noisy, OCR. We could, of course, cache this, open it, and pass it around as a parameter, but it's okay for a demonstration to do it this way. And then we'll send in the threshold value, which will be 0 the first time, 64 the second time, and so forth. And let's use Tesseract on it. It's inefficient to binarize it twice, but this is really just for a demo. So here we'll call print the py-tesseract.image-to-string, passing in then a call to binarize, which passes in a call to image.open. So there's a lot of image.opens here, lots of room. This code could be improved, but it should generate an example for us. So you can see the result with threshold 0 is pretty empty. With threshold 64, we actually get a very faint looking image, but it seems like we get all of or most of the text. When we increase the threshold to 192 from 128, we see that we actually pick up a new space between the words of and this, so we're getting more definition in the text. But then when we increase the threshold all the way to 256, we lose a lot of text because a whole segment of the image becomes black. And then all of a sudden at the very top end threshold, we get nothing because the whole image is black at that point. We could see from this that a threshold of 0 essentially turns everything white, that the text becomes more bold as we move towards a higher threshold, and the shapes, which have a filled-in gray color, become more evident at higher thresholds. In the next lecture, we'll look a bit more at some of the challenges you can expect when doing OCR on real data. Let's try a new example and bring together some of the things that we've learned. Here's an image of a storefront. Let's load it and try and get the name of the store out of that image. So from PIL, we'll need the image package, of course, and then let's bring in py-tesseract as well. So let's read in the storefront image I've loaded into the course and display it. So I put this in the read-only/storefront.jpg, and we'll just open that as an image and display it in line. And then finally, let's try and run Tesseract on that image and see what the results are. So we'll call image-to-string on that. We see at the very bottom that there's just an empty string. Tesseract is unable to take this image and pull out the name. But we learned how to crop an image in the last set of lectures, so let's try and help Tesseract by cropping out certain pieces. So first we have to set the bounding box. In this image, the store name is in a box bounded by roughly 315, 170, 700, and 270. So I'll make a bounding box equal to this tuple. Remember, that's the upper left corner, and then we walk around the image. And you can go back to the PIL lecture if you want to be reminded how to do this. Now let's crop the image. So we just call the image.crop and we pass in a bounding box. And it doesn't change the image, it returns a new image. So we save this to this title image variable that we'll use later. Now let's display it and pull out the text. So we'll pull out display, and then we'll call py-tesseract.image-to-string and pass in the title image. Great. So we see how with a bit of problem reduction we can make that work. So now we've been able to take an image, pre-process it where we expect to see text, and turn that text into a string that Python can understand. If you look back up at the image though, you'll see that there's a small sign inside of the shop, and that also has the shop name on it. I wonder if we're able to recognize the text on that sign. Let's give it a try. First, we need to determine a bounding box for that sign. I'm going to show you a shortcut to make this easier in an optional video in this module, but for now, let's just use the bounding box that I decided on. So the bounding box, we'll set this to a tuple of 900 by 420 for the upper left, and then 940 by 445 for the lower right. Now let's crop the image. And so we just call image.crop, pass it in the bounding box, and we'll call this little sign for fun, and display that little sign. All right, this is a little sign. OCR works better with higher resolution images, so let's increase the size of this image by using the pillow resize function. Let's set the width and the height equal to 10 times the size it is now in a W, H tuple. So we'll take the new size and we'll make it equal to the little sign dot width times 10 and the little sign dot height times 10. Now let's check the docs for resize. We can see here that there's a number of different filters for resizing the image. The default is image.nearest. Let's see what that looks like. So we'll take our little sign.resize, we'll pass in the new bounding box size, so that's new size, and then we'll say image.nearest all in caps and pass that to display. So here you can see that it actually resized the image, and now it's maybe much more readable. I don't know, I didn't have troubles maybe seeing it before, although it was little, and it says the word fossil. I think we should be able to find something better though. I can read this, but it looks really pixelated. Let's see what all the different resize options look like. You can go back up to the documentation to look at the names. So here I'm going to make just a list of all the different names as options. So image.nearest, image.box, image.bilinear, image.hamming, image.bicubic, and image.lanoche is how you say that. So for each of the options, I'm just going to iterate over these. Let's print out the option name. So we'll print out whatever the option name is, and then let's display what this option looks like on our little sign. So here we're actually going to call little sign.resize, pass in the new size, pass in the option that we're looking at, and call to display. Okay, so you can see that this has run, and we have a whole bunch of different numbers are printed, and then different images that are interesting. So from this we can notice two things. First, when we print out one of the resampling values, it actually just prints an integer. And this is actually really common, that the API developer writes a property, such as image.bicubic, and then assigns it to an integer value to pass it around. Some languages use enumerations of values, which is common in, say, Java. But in Python, this is a pretty normal way of doing things. The second thing we learn is that there's a number of different algorithms for the image resampling. In this case, the Lanoche and image-bicubic filters do a good job. Everything else not so much. So let's see if we're able to recognize the text off this resized image. So first, let's resize to the larger size. So I'm going to create something bigger sign, and I'm going to take little sign.resize. I'm going to pass in our new size that we want, and then I'm going to use image.bicubic for lack of any personal preference. You feel free to try one of the different methods. And then let's print out the text. So we'll call py-tesseract image to string and pass in the bigger sign. Well, not really any text there. Let's try and binarize this. So first, let me just bring in the binarization code we did earlier. Now, let's apply binarizations with, say, a threshold of 190 and try and display that as well as to do the OCR work. So binarize, remember this function takes in the sign or the image, I guess, that we want to binarize, and then a value between 0 and 255. And it's going to walk through pixel by pixel of the image and either set it to 0 or 1. So change it to straight up black and white. And then we'll display what the binarized sign looks like. And then let's actually try and get the text out with py-tesseract too, in the hopes that 190 is actually a good number for us to use. Well, that looks pretty abysmal, I would say. It doesn't look at all like fossil. I guess you could kind of see some of the S's there, but really not much in that image at all. Okay, so the text is pretty useless. How should we pick the best binarization to use? And there's a number of different methods, but let's just try something very simple to show how this can work. We have an English word that we're trying to detect. It's called fossil. If we tried all binarizations from 0 through 255 and looked to see if there were any English words in that list, this might be one way. So let's see if we could write a routine to do this. So we're problem solving on our own here. So first, let's load a list of English words into a list. I put a copy in the read-only directory for you to work with. So we'll create something, an indict, it's just an empty list. And then I'm going to open the read-only words alpha.txt as read. You can go back into one of the previous courses if this doesn't look very familiar to you on how to work with files. We're going to call the file f. And then I'm just going to read all of f in one giant chunk and put that in data. So now we actually want to split this into a list based on those new line characters. If you go look in that data file, words alpha, you'll see it's one word per line. So I'll call data.split on /n. This is the new line character, and this will return a new list, which is all of the different words, and I'll put this into English Dictionary. Now, let's iterate through all the possible thresholds and look for an English word, printing it out if it exists. So for I in range 150 and 170, I'm just going to binarize between those ranges. Let's binarize and convert this to string values. And then string we'll set to py-tesseract.image to string. So we'll binarize, passing in the bigger sign and our given I value. So this will binarize with 150, 151, 152, 153, and so forth. So we're going to try them all between these two threshold values, 150 and 170. So we want to remove all non-alphabetical characters. So that includes parentheses, brackets, percentage signs, dollar signs, etc. from the text. So here's a short method to do that. So first let's convert our string to lowercase only. So string.lower, and we'll just change string. And then let's import the string package. It's got a nice list of lowercase characters. So import string. And now let's just iterate over our string, looking at it character by character, putting it in the comparison text. So we'll create some new value comparison, and then for every character in our string, remember this is a lowercase, if that character is in the string.ascii lowercase, so this is actually just checking to see if a single character is in a list of characters. And remember, a string and a list of characters are the same when you use in. And if so, then comparison is equal to comparison plus that character. So we just append it to our output string. All right, finally, let's search for the comparison in the dictionary file. So that's easy in Python. In other languages, you would have to do a lot of work. But here we just use the in comparator and see if comparison is indict. And then we're going to print it out if we find it. And so we'll print comparison. All right, let's run that. So you should start to see that various characters come up. And in my case, fossil came up and W came up. So W is also in this dictionary, and a W was detected in data that we sent in at least one of the binarizations. So, well, this is not perfect, but we can see fossil there among other values. And this is not a bad way actually to clean up OCR data. It can be useful to use a language or domain-specific dictionary in practice instead of all of the English language words, especially if you're generating a search engine for specialized language, such as medical knowledge base or locations, so like cities. And if you scroll up and look at the data we're working with, this tiny little wall hanging in the inside of a store is really not so bad. A lot of this comes down to the purpose that you're actually doing the OCR for. So if you're using it, for instance, to back a search engine, that's one thing. If you're using it to do text-to-speech, for instance, and somebody's going to use this to listen to a lecture, that's completely different. And you have to have a very, very strong method for generating the actual data. So at this point, you've now learned how to manipulate images and convert them into text. In the next module in this course, we're going to dig deeper, further into a computer vision library, which allows us to detect faces, among other things. So then we'll go on to a culminating project. I'll see you there. In this brief lecture, I want to introduce you to one of the more advanced features of the Jupyter Notebook development environment, called widgets. Sometimes you want to interact with a function you've created and call it multiple times with different parameters. For instance, if we wanted to draw a red box around a portion of an image to try and fine-tune the crop location, Widgets are one way to do this quickly in the browser without having to learn how to write a whole large desktop application. Let's check it out. First, we want to import the image and image draw classes from the Pillow package. So from Pill, we'll bring in image and image draw. Then we want to import the interact class from the widgets package. So from ipywidgets, so this is included automatically because we're using the IPython interpreter, we'll bring in interact. We will use interact to annotate a function. Let's bring in an image that we know we're interested in, like the storefront image from a previous lecture. So we'll bring that in from read only and save that into the image object. Okay, so our setup is done. Now we're going to use the interact decorator to indicate that we want to wrap the Python function. We do this using the @ sign. This will take a set of parameters which are identical to the function to be called. Then Jupyter will draw some sliders on the screen to let us manipulate those values. Decorators, which again is the @ sign is describing this, are standard Python statements and just a shorthand for functions which wrap other functions. They're a bit advanced though, so we haven't talked about them in this course, and you might just have to have some faith. So we do @ interact. This is our annotation, our decorator, and we're going to put in 4 values. So we'll give it the left and the top. I'll set the defaults for these at 100, and the right and the bottom. And so this is where we actually want to draw our red box. So now we just write the function as though we had it before. So def draw border, again, it's got to take the exact same parameters as the decorator. So left, top, right, bottom. We'll make a copy of the image. So we're working here with a global image, and we're just making a copy. We'll create a drawing object based on the image that we've made a copy of. And then we'll draw a rectangle. And so we'll just pass in the left, top, right, bottom. And we'll set the fill to none and the outline to red. And you can go back and look in the Pill lectures if this doesn't look so familiar to you. And then we'll just display it in line. Let's execute that. And so here we have that we actually have our storefront image. We have 4 sliders, left, top, right, and bottom. You'll see that as we take one of these and we drag them over, it changes. So this is changing the left-hand side if we wanted to. If we take the top, or why don't we take the right and stretch this out a bit so you can see that we can stretch that out. You'll see that it's a little laggy. That's actually, there's a lot of documentation about how to use these well, and there's ways that you can speed it up so it's not doing all these intermittent values. But I essentially just did this and built out my my sliders nicely so that I could actually just pull out the text that I was interested in. So Jupyter Widgets is certainly advanced territory, but if you'd like to learn more to explore, you can check out the website for IPython widgets at Read the Docs. And I would encourage you to do so and play with this nice platform for doing Python. The next library we're going to look at is called Kraken, which was developed by the Université PSL in Paris. It's actually based on a slightly older code base, Octopus, and you can see how the flexible open source licenses allow new ideas to grow by building upon older ideas. And in this case, I fully support the idea that the Kraken, a mythical massive sea creature, is the natural progression of an octopus. What we're going to use Kraken for is to detect lines of text as bounding boxes in a given image. The biggest limitation of Tesseract is the lack of a layout engine inside of it. Tesseract expects to be using fairly clean text. It gets confused if we don't crop out other artifacts. It's not bad, but Kraken can help us by segmenting pages. Let's take a look. First, we'll take a look at the Kraken module itself. So import Kraken. Then let's run help on Kraken. So there isn't much of a discussion here, but there are a number of submodules that look interesting. I spent a bit of time on their website, and I think the page seg module, which handles all of the page segmentation, is the one we want to use. Let's look at it. So from Kraken, we'll import page seg, and then help on page seg. So it looks like there are a few different functions that we can call, and the segment function looks particularly appropriate. I love how expressive this library is on the documentation front. I can see immediately that we're working with pill.image files, and the author has even indicated that we need to pass in either a binarized, example 1, or grayscale, example L for luminance, image. We can also see that the return value is a dictionary object with two keys. Text direction, which will return to us a string of the direction of text, and boxes, which appears to be a list of tuples, where each tuple is a box in the original image. Let's try this on the image of text. I have a simple bit of text in a file called tocall.png, which is from a newspaper on campus here. So from pill, we'll import image as normally, and then image.open in read-only /tocall.ping. Let's display the image in line. So we'll just call it display with IM. And let's now convert it to black and white and segment it up into lines with Kraken. So for this, we'll make some new variable bounding boxes is equal to pageseg.segment, and then im.convert, and we'll binarize that sub boxes. And let's print those lines to the screen. So I'll just print bounding boxes. All right, so we see the image here, and we see the bounding boxes. Okay, so pretty simple two-column text and then a list of lists, which are the bounding boxes of the lines of that text. Let's write a little routine to try and see the effects a bit more clearly. I'm going to clean up my act a bit and write real documentation too. It's good practice. So def show boxes, we'll call it, and we'll take in a parameter image. So the docs, I say, modifies the past image to show a series of bounding boxes on an image is run by Kraken. Our parameter image is a pill.image object. That makes it easier for other people to use this function. And our return is also going to be an image, the modified pill.image object. Okay. Let's bring in our image draw object first. So from pill import image draw. And this was covered in earlier lectures. You can go back if you're interested. And let's grab a drawing object to annotate that image. So we'll create some new variable, drawing object, image draw.draw, and we'll pass in the image that we want to be able to draw it. We can create a set of boxes using the pageseg.segment. So bounding boxes is equal to pageseg.segment. We'll convert our image. Remember, we have to binarize our luminance as sub-boxes. And now let's go through that list of bounding boxes. So for box and boxes, we're just going to draw a nice rectangle. So drawing object.rectangle, we'll give it the box we're interested in. We'll set the fill to none and the outline to red. And to make it easy, we're just going to return that image object. So return img. To test this, let's use display. So here, display, then show boxes, then we'll read in the image, image.open. We could, of course, reuse the image, but this is good practice when you're using Jupyter notebooks. All right, so we see our image here with a bunch of red boxes. So not bad at all. It's interesting to see that Kraken isn't completely sure what to do with this two-column format. In some cases, Kraken has identified a line in just a single column, while in other cases, Kraken has spanned the line marker all the way across the page. Does this matter? Well, it really depends on our goal. In this case, I want to see if we can improve on this a little bit. So we're going to go a bit off script here. While this week of lectures is about libraries, the goal of this last course is actually to give you confidence that you can apply your knowledge to actual programming tasks, even if the library you're using doesn't quite do what you want. I'd like to pause the video for a moment and collect your thoughts. Looking at the image above, with the two-column example in red boxes, how do you think we might modify this image to improve Kraken's ability to detect lines? So thanks for sharing your thoughts. I'm looking forward to seeing the breadth of ideas that everyone in the course comes up with. Here's my partial solution. When looking through the Kraken docs on the pageseg function, I saw that there are a few parameters we can supply in order to improve the segmentation. One of these is the black colceps parameter. If set to true, Kraken will assume that the columns will be separated by black lines. This isn't our case here, but I think we can have all of the tools that we need to go through and actually change the source image to have a black separator between columns. So the first step is what I want to update the showBoxes function. I'm going to just do a quick copy and paste from above, but add in the black call seps equals true parameter. Okay, the next step is to think of the algorithms that we want to apply to detect a white column separator. In experimenting a bit, I decided that I only wanted to add the separator if the space was at least 25 pixels wide, which is roughly the width of a character, and 6 lines high. The width is easy. Let's just make a variable, so car width equals 25. The height is harder since it depends on the height of the text. I'm going to write a routine to calculate the average height of a line. So def calculate line height, and we'll pass it in the image. So our docs for this calculates the average height of a line from a given image. We'll take a pill.image object, and we'll return the average height of a line in pixels. Let's get a list of the bounding boxes for this image. So we'll convert this using pageseg.segment. Remember, binarize always, and we just want to pull out the boxes. Each box is a tuple of top, left, bottom, right. So the height is just top minus bottom. So let's just calculate this over the set of all boxes. So we'll set some height accumulator to be 0 for box and bounding boxes, and then the height accumulator is equal to the height accumulator plus box sub 3 minus box sub 1. This is a bit tricky. Remember that we start counting in the upper left corner in pill. So for those of you who are used to starting in the lower left corner, not true with images. We start in the upper left normally. Now let's just return the average height. And let's change it to the nearest full pixel by making it an integer. So we'll just return and we'll typecast this to an integer, which will just cause rounding, and height accumulator divided by the number of bounding boxes. And let's test this with the image that we've been using up till now. So line height equals the calculated line height of image.open read-only / toCall.ping, and we'll just print out the line height. Okay, so the average height of a line is 31 pixels. Now, we want to scan through the image, looking at each pixel in turn to determine if there is a block of white space. How big of a block should we look for? That's a bit more of an art than a science. Looking at our sample image, I'm going to say an appropriate block should be 1 character width wide and 6 line heights tall. But honestly, I just made this up by eyeballing the image, so I would encourage you to play with the values as you explore. Let's create a new box called gap box that represents this area. So gap box is equal to 0, 0, and then our car width, and then our line height times 6. Let's just look at that gap box. It seems we'll want to have a function which, given a pixel in an image, can check to see if that pixel has white space to the right and below it. Essentially, we want to test to see if the pixel is in the upper left corner of something that looks like the gap box. If so, then we should insert a line to break up this box before sending it to Kraken. Let's call this new function gapCheck. So def gapCheck will pass in an image and a location. So here are docs, checks the image in a given XY location to see if it fits the description of a gap box. Our first parameter is a pill.image file. Our second parameter, location, is a tuple xy, which is a pixel location in that image. So we're not going to pass x and y separately. We're going to pass xy together in a tuple. We're going to return true if that fits the definition of a gap box. Otherwise, we'll return false. Recall that we can get a pixel using the image.getPixel function from pill. It returns the value as a tuple of integers, 1 for each color channel. Our tools all work with binarized images, black and white, so we should just get one value. If the value is 0, it's a black pixel. If it's white, then the value should be 255. We're going to assume that the image is in the correct mode already, in that it already is binarized. The algorithm to check our bounding box is fairly easy. We have a single location, which is our start, and then we want to check all the pixels to the right of that location up to gap box sub 2. So for x in range, location sub 0, so that's our x value, to location sub 0 plus gap box sub 2, so that's our offset. And the height is basically the same, so let's iterate a y variable to gap box sub 3. So for y in range, location sub 1, to location sub 1 plus gap box sub 3. We want to check if the pixel is white, but only if we're still within the image. So if x is less than the image.width and y is less than the image.height. If the pixel is white, we don't want to do anything. If it's black, we just want to finish and return false. So if image.getPixel xy is not equal to 255, then we'll return false. If we've managed to walk through the whole gap box without finding any non-white pixels, then we can return true. This is actually a gap, so we'll just return true. All right, we have a function to check for a gap called gapCheck. What should we do once we find a gap? For this, let's just draw a line in the middle of it. Let's create a new function. So def, I'll call this drawSep, and it'll take an image and a location. And this draws a line in the image, in the middle of a gap discovered in the location. Note that this doesn't draw the line in the location, but draws it at the middle of the gap box, starting at the location. So the first parameter is a pil image file, and then a tuple xy, which is the pixel location. So first, let's bring in all of our drawing code. So from pil, we'll import draw, and then we'll create a drawing object, which equals imageDraw.drawImage. Next, let's decide what the middle means in terms of coordinates in the image. So x1 is equal to location sub 0 plus, and then we'll just take our gap box size, x size divided by 2 and round it to an int. And our x2 location's actually just the same thing, since this is a 1 pixel vertical line. So we'll just say x2 is equal to x1. Our starting y coordinate is just the y coordinate that was passed in, which is the top of the box. So y1 equals location sub 1. But we want our final y coordinate to be the bottom of the box. So y2 is equal to y1 plus the gap box height, which is gap box sub 3. And then we'll actually do the work. Drawing object.rectangle, we'll pass in x1, y1, x2, y2, set the fill to black. Here I'll set the outline to black. And that'll draw us a nice rule that's a vertical rule. And we don't have anything we need to return from this because we actually modify the image directly in line. All right, now let's try it out. This is pretty easy. We can just iterate through each pixel in the image, check if there's a gap, then insert a line if there is. So def process image, take an image. So we're going to take in an image of text and add this black vertical bars to break up columns. Pil.image file, both in and out. We're going to start with a familiar iteration process. So for x in range width and for y in range height, we're going to check to see if there's a gap at this point. So if gapCheck if gapCheck and then we'll pass it the image and the tuple is true, then we're going to update the image and draw a separator in it. So then we'll just call our drawSep image xy. And for good measure, we'll return the image we modified. So return image. All right, let's test it out. Let's read in our test image and convert it through the binarization process. So I is our new image. We'll read this in and we'll convert it to luminance here. And then we're going to call process image. And then since we returned it, we're going to call display image. Now, you can notice immediately that this function didn't return right away. In fact, you're sitting there kind of wondering what's happening, and you can see the asterisks in the margin in Jupyter, and that tells you that the backend processor is still working. And this will actually take a fair bit of time on the Coursera system. And so reflect a little bit on what's happening in the code that we've written. We're iterating over every pixel in the image, both through the X and Y directions. And we're looking to see if there's a gap box to the right and to the lower side of that pixel. And then we're going to try and draw a line if there is. And then we just go immediately to the next pixel. So you can see there's lots of opportunities for optimization of this code. It's really just meant to be a demonstration of what you can do yourself when you start combining these libraries. We're going to use the magic of video to speed this up a little bit for you for the video lecture, but if you're following in the Jupyter notebooks, and I hope that you are, please think about how you might change that to modify the image. Not bad at all. The effect at the bottom of the image is a bit unexpected to me, but it makes sense. You can imagine that there's several ways we might try and control for this, but let's see how this new image works when we try and run it through the Kraken layout engine. So we'll say display, show boxes, and because we stored I, it makes it easy. So it looks like that's actually pretty accurate and fixes the problems we faced. Feel free to experiment with different settings for the gap heights and width and share in the forums. You'll notice through this method, it's really quite slow, which is a bit of a problem if we wanted to use this on larger text. But I wanted you to see how you could mix your own logic and work with libraries you're using. Just because Kraken didn't work perfectly doesn't mean we can't build something more specific to our use case on top of it. I want to end this lecture with a pause and ask you to reflect on the code we've written here. We started this course with some pretty simple use of libraries, but now we're digging in deeper and solving problems ourselves with the help of libraries. Before we go to our last library, how well prepared do you think you are to take your Python skills out into the wild? OpenCV supports reading of images in most file formats, such as JPEGs, PNGs, and TIFF. Most image and video analysis requires converting images into grayscale first. This simplifies the image and reduces noise while allowing for improved analysis. Let's write some code that reads in an image of a person, Floyd Mayweather, and converts it into grayscale. So first we're going to import the OpenCV package CV2. So import CV2 as CV. And then we'll load the Floyd.jpg image. So image equals cv.read from read-only Floyd.jpg. And we'll convert it to grayscale using this CV color image. So gray equals cv.cvt color. This is a function in OpenCV, pass in the image, and then cv.color bgr to gray. Now, before we get to the result, let's talk about the docs. Just like Tesseract, OpenCV is an external package written in C++, and the docs for Python are really poor. This is unfortunately quite common when Python is being used as a wrapper. Thankfully, the web docs for OpenCV are actually pretty good, so hit the website at docs.opencv.org when you want to learn more about a particular function. In this case, CVT color converts from one color space to another, and we're converting our image to grayscale. Of course, we already know at least two different ways of doing this, using binarization and PIL color space conversions. So let's inspect this object that has been returned. So import inspect, this is in the standard library, and inspect.getMRO, and then type of gray. So we see that this is a type of ND array, which is a fundamental list type coming from the numerical Python project. That's a bit surprising. Up until this point, we've been used to working with these pil.image objects. OpenCV, however, wants to represent an image as a two-dimensional sequence of bytes, and the ND array, which stands for an n-dimensional array, is the ideal way to do this. Let's look at the contents of the array, so just gray. So the array is shown here as a list of lists, where the inner lists are filled with integers. The dtype equals uint8 definition indicates that each of the items in the array is an 8-bit unsigned integer, which is very common for black and white images. So this is a pixel by pixel definition of the image. The display package, however, doesn't know what to do with this image. So let's convert it into a PIL object to render it into the browser. So from PIL, import image. PIL can take an array of data with a given color format and convert this into a PIL object. And this is perfect for our situation, as the PIL color mode, L, is just an array of luminance values in unsigned integers. So the new image equals image.fromArray, gray, and then we tell it luminance values. Then display image. Let's talk a bit more about images for a minute. NumPy arrays are multidimensional. For instance, we can define an array in a single dimension. So import NumPy as MP, and then singledim equals mp.array, and we just pass into this a list of all of the integer values. In an image, this is analogous to a single row of 5 pixels, each in grayscale. But actually, all imaging libraries tend to expect at least 2 dimensions, a width and a height, and to show a matrix. So if we put the single dim inside of another array, this would be a 2-dimensional array with the equivalent of 1 element in the height direction and 5 in the width. So we can go double dim equals np.array, and here we've just taken the single dimension array and put it inside another bracket. And so double dim. So this should look pretty familiar. It's a lot like the lists of lists we saw above. Let's see what this new 2-dimensional array looks like if we actually display it to the screen. So display, and then we have to convert to pil, so image.fromArray. We pass in the double dim and say that it's a luminance, and this should display it to the screen. So that's pretty unexciting. It's just a little line. It's actually 5 pixels in a row, to be exact, of different levels of black. The NumPy library has a nice attribute called shape that allows us to see how many dimensions big an array is. The shape attribute returns a tuple that shows the height of the image by the width of the image. So double dim dot shape. Let's take a look at the shape of our initial image that we loaded into the image variable. So img.shape. This image has 3 dimensions. That's because it's got a width, a height, and what's called a color depth. In this case, the color is represented as an array of 3 values. Let's take a look at the color of the first pixel. So the first pixel is equal to image sub 0 on the width, sub 0 on the height. And so the first pixel. Here we see that the color value is provided in full RGB using an unsigned integer. This means that each color can have one of 256 different values, and that the total number of unique colors that can be represented by this data is 256 by 256 by 256, which is roughly 16 million colors. We call this 24-bit color, which is 8 plus 8 plus 8, 24. If you find yourself shopping for a television, you might notice that some expensive models are advertised as having 10-bit or even 12-bit panels. These are televisions where each of the red, green, and blue color channels are represented by 10 or 12 bits instead of 8. For 10-bit panels, this means that there's over 1 billion colors capable, and 12-bit panels are capable of over 68 billion colors. We're not going to talk much more about color in this course, but it's a fun subject. Instead, let's go back to this array representation of images, because we can do some interesting things with this. One of the most common things we can do with an ND array is to reshape it, to change the number of rows and columns that are represented here so that we can do different kinds of operations. Here's our original 2-dimensional image. So let's print original image and then print out gray. If we wanted to represent that as a 1-dimensional image, we just call reshape. So print new image. And reshape takes the image as the first parameter and a new shape as the second. So we'll say image 1D equals np.reshape. We send in our original array, gray, and then the new shape we'll have as 1, and then gray.shape times gray.shape sub 0 and 1. Multiply them together, you get the total number of pixels. And then print image 1D. So why are we talking about these nested arrays of bytes when we're supposed to be talking about OpenCV as a library? Well, I wanted to show you that often libraries work on the same kind of principles. In this case, that images are stored as arrays of bytes, and they're not representing the data in the same way in their APIs. But by exploring a bit, you can learn how the internal representation of data is stored and build routines to convert between formats. For instance, remember the last lecture when we wanted to look for gaps in an image so we could draw lines to feed into Kraken? Well, we use pil to do this using the getPixel to look at the individual pixels and see what luminosity values were, then image.draw.rectangle to actually fill in a black bar separator. This was a nice high-level API and let us write some routines to do the work we wanted without having to understand too much about how the images were actually being stored. But computationally, it was very slow. Instead, we could write the code to use this using matrix features within NumPy. Let's take a look. So import CV2 as CV. We'll load the 2-column image as well, so image equals cv.read and read-only 2-col. And we'll convert it to grayscale using this CVT color image. So gray equals cv.cvt color image and color to gray. Now, remember how slicing on a list works. If you have a list of a number such as a equals 0 through 5, and then you go a sub 2 colon 4, that's going to return a list of numbers at positions 2 through 4 inclusive. And don't forget that lists start indexing at 0. If we have a two-dimensional array, we can slice out a smaller piece of that using the format a sub 2 comma 4 for the first dimension, and then 1 colon 3 for the second dimension. And you could think of this as first slicing along the row dimension, then in the columns dimension. So in this example, that would be a matrix of rows 2 and 3 and columns 1 and 2. Here's a look at our image. So gray, 2 colon 4, and 1 colon 3. So we see that it's all white. We can use this technique as a window and move it around our big image. Finally, the ND array library has lots of matrix functions, which are generally very fast to run. One that we might want to consider in this case is count non-zero, which just returns the number of entries in the matrix which are not zero. So np.count non-zero, we can say gray and give it 2 colon 4 and 1 colon 3. And so this is going to crop out essentially a piece of the image and as a matrix and send it to np.count non-zero. Okay, the last benefit of going to this low-level approach to images is that we can change pixels very fast as well. Previously, we were drawing rectangles and setting a fill and line width. This is nice if you want to do something like change the color of the fill from the line or draw complex shapes like polygons. But we really just wanted a line here, and that's really easy to do. All we have to do is change the number of luminosity values from 255 to 0. Here's an example. Let's create a big white matrix. So white matrix equals, and we'll use np.full. We wanted a 12 by 12 matrix, so we'll pass that in as the tuple for the shape of it. 255 because we want everything to be white, and we'll set the dtype to be np.uint8. So that means 1 byte per pixel to describe it. Now let's display that. So remember, we have to do image.fromArray to convert from pill. Pass in the white matrix, tell pill that it's luminosity values. And let's print out the white matrix as well. So this looks pretty boring. It's just a giant white square which we actually can't see. But if we want, we can easily color a column to be black. So if we go white matrix sub, and here I just want all row values, so I just use a colon, comma 6, so I want the 6th, in this case the 7th column, and I want to set this to be np.full, and I just want to add in a matrix of 1 colon 12 in shape with 0 that's also dtype int. And I want to display this to the screen, so image.fromArray white matrix, which now won't just be white, and then print out the white matrix. And that's essentially what we wanted to do. So why should we do it this way when it seems so much more low level? And really the answer is speed. This paradigm of using matrices to store and manipulate bytes of data for images is much closer to how low-level API and hardware developers think about storing files and bytes in memory. How much faster is this? Well, that's up to you to discover. There's an optional assignment for this week to convert our old code over into this new format, to compare both the readability and the speed of the two different approaches. Okay, we're just about at the project for this course. If you reflect on the specialization as a whole, you'll realize that you started with probably little or no understanding of Python, progressed through the basic control structures and libraries included with the language with the help of a digital textbook, moved on to more high-level representations of data and functions with objects, and now started to explore third-party libraries that exist for Python, which allow you to manipulate and display images. This is really quite an achievement. You've also no doubt found that as you've progressed, the demands on you to engage in more self-discovery have also increased. Where the first assignments were maybe straightforward, the ones in this week require you to struggle a bit more with planning and debugging code as you develop. But you've persisted, and I'd like to share with you just one more set of features before we head over to the project. The OpenCV library contains mechanisms to do face detection on images. The technique used is based on Haar cascades, which is a machine learning approach. Now, we're not going to go into the machine learning bits. We have another specialization on that called the Applied Data Science with Python specialization. And you can take that after this one if you're interested. But here we're going to treat OpenCV more like a black box. OpenCV comes with trained models for detecting faces, eyes, and smiles, which we'll be using. You can train models for detecting other things like hot dogs or flutes. And if you're interested in that, I'd recommend you check out the OpenCV docs on how to train a cascade classifier, and here's a URL. However, in this lecture, we just want to use the current classifiers to see if we can detect portions of an image which are interesting. So the first step is to load OpenCV and the XML-based classifiers. So import CV2 as CV, and then we'll create a face cascade classifier. So cv.cascade classifier, and we'll load that from read-only. I've put it in there, Haar cascade frontal face default.xml. Okay, with the classifiers loaded, we now want to try and detect a face. Let's pull in the picture we played with the last time. So image equals cv.imread, and we'll bring in the Floyd picture. And we'll convert it to grayscale using the CVT color image. So gray equals cv.cvt color, and we convert this to grayscale. The next step is to use the face cascade classifier. I'll let you go explore the docs if you'd like to, but the norm is to use the detect multiscale function. This function returns a list of objects as rectangles. The first parameter is an ND array of the image. So faces equals face cascade dot detect multiscale, and we just pass it in our ND array, our image gray. And now let's just print those faces out to the screen. And we'll print them out as a list. The resulting rectangles are in the format of X, Y, W, H, where the X and Y denote the upper left-hand corner point for the image, and the width and height represent the bounding box. We know how to handle this already in PIL. So from PIL, import image. Let's create a PIL image object. So PIL image equals image.fromArray. We pass in gray, and we set the mode to luminosity. Now, let's bring in our drawing object. So from PIL, import image draw. And let's create a context. So drawing equals imageDraw.draw and pass in the PIL image. Now let's pull the rectangle out of the faces object. So we'll take a rectangle and faces to the list. We know there's one item in there, so sub-0. And now we're just going to draw a rectangle around the bounds. So drawing.rectangle, pass in the rectangle we're interested in, set the outline to white, and display the image in line. So display PIL image. So, not quite what we're looking for. What do you think went wrong? Well, a quick double check of the docs, and it's apparent that OpenCV is returning the coordinates as x, y, w, h, while pil.imageDraw is looking for x1, y1 and x2, y2. So it looks like this is an easy fix. So let's wipe our old image. So PIL image, and we'll just reload our image, set up our drawing context, and draw the new box. So drawing.rectangle, and so we'll take rec sub 0 and rec sub 1, and then we'll add to that rec sub 2 and rec sub 3 as appropriate and set our outline. And display it in line. Okay, we see the face detection works pretty good on this image. Note that it's apparent that this is not head detection, but that the Haar cascades file that we're using is for eyes and a mouth. Let's try this on something a little bit more complex. Let's read in that MSI recruitment image. So image equals cv.imread, and we'll bring in the MSI recruitment.gif. And let's take a look at that image to remind ourselves what it looks like. So display image.fromArray. Remember, we have to do this, but we don't have to pass in luminosity values because it's in full color. Whoa, what's that error about? Looks like there's an error on a line deep within the pill-image.py file, and it's trying to call an internal private member called dunder array underscore interface dunder on the image object, but this object is none. It turns out that the root of this error is that OpenCV can't work with GIF images. This is kind of a pain and unfortunate, but we know how to fix this, right? One way is that we could just open this in pill and then save it as a ping and then open that in OpenCV. So let's use pill to open our image. So pill image equals image.open and bring in our GIF. Now let's convert it to grayscale for OpenCV and get the byte stream. So OpenCV version is equal to pill image.convert luminosity, and that's going to return to us an array. And now let's just write that out to a file. So OpenCV version.save MSI recruitment.ping. Okay, now that the conversion of format is done, let's try reading this back into OpenCV. So OpenCV image equals cv.imread and bring in the ping. We don't need to color convert this because we saved it as grayscale. Let's try and detect faces in that image. So faces equals face cascade.detect multiscale and pass in the ND array CV image. Now we still have our pill color version in a GIF. So pill image equals image.open the GIF. And so we'll set a drawing context. So drawing equals imageDraw.draw. Now for each line in faces, let's surround it with a red box. So for X, Y, W, and H in faces. So this might actually be new syntax for you. Recall that faces is a list of rectangles in the X, Y, width, and height format. That is a list of lists. Instead of having to do an iteration and then manually pull out each item, we can use something called tuple unpacking to pull out individual items in the sublist directly to variables. This is a really nice Python feature. All right, so now we just need to draw our box. So drawing.rectangle, x, y, and then x plus width, can't forget this, and y plus height, and set the outline to white, and display pill.image. Whoa, what happened here? We see that we've detected faces, so there's some white boxes, and that we've drawn boxes around them, but the colors have gone all weird. This, it turns out, has to do with the color limitations for GIF images. In short, a GIF image has a very limited number of colors. This is called a color palette, after the palette artists used to mix paints. For GIFs, the palette can only be 256 colors, but they can be any 256 colors. When a new color is introduced, it has to take the space of an old color. In this case, pill adds white to the palette, but doesn't know which color to represent, and thus messes up the image. Who knew there was so much to learn about image formats? We can see what mode, though, an image is with the .mode attribute. So if we do pill image.mode, we can see that there's a list of modes in the pillow documentation, and they correspond with the color spaces that we've been using. For the moment, though, let's just change back to RGB, which represents a color as a 3-byte tuple instead of in a palette. So let's read in our image, bring back our GIF image nice and clean. Let's convert it to RGB mode. So that's pretty easy. We just do pill.image.convert with RGB. And let's print out this mode. Okay, we're pretty convinced that we've changed it. Now let's go back to drawing rectangles. Let's get our drawing object. And let's iterate through the face sequence again. And we'll tuple unpack as we go. So x, y, width, and height in faces. And remember, again, width and height, so we have to add these appropriately. So drawing rectangle, x, y, x plus width, y plus height, set the outline to white. Finally, let's display that image to the screen. Awesome. We managed to detect a bunch of faces in that image. It looks like we've missed 4 faces. In the machine learning world, we would call these false negatives, something which the machine thought was not a face, so a negative, but that it was incorrect on. Consequently, we would call the actual faces that were detected as true positives, something that the machine thought was a face and it was correct on. This leaves us with false positives, something the machine thought was a face but it wasn't. We can see that there's 2 of these in the image, picking up the shadow patterns or textures in shirts and matching them with haar cascades. Finally, we have a class of true negatives, or the set of all possible rectangles that the machine learning classifier could consider where it correctly indicated that the result was not a face. In this case, there's many, many, many true negatives. There's a few ways we could try and improve this, and really it requires a lot of experimentation to find good values for a given image. First, let's create a function which will plot out rectangles for us in the image. So def show recs will have that pass in faces. Let's read in our GIF and convert it. So we'll read it in and we'll convert it to RGB in the same line. We'll set our drawing context, and we'll plot all of the faces or all of the rectangles in faces. So for X, Y, width, and height in faces. And we've seen this before with drawing.rectangle, and we'll set the outline to white. And finally, we'll display this. All right, so now we have a function show faces. So first up, we could try and binarize this image. And it turns out that OpenCV has a built-in binarization function called threshold. You simply pass in the image, the midpoint, and the maximum value, as well as a flag which indicates whether the threshold should be a binary or something else. So let's try this. So we'll do CV image bin equals CV.threshold. So we pass in the image we're interested in. I'll choose 120 for our threshold, 255 for our top end, and then CV.thresh binary. And we're just going to pull from this actually sub 1 because this function returns a list and we want the second value. Now let's do the actual face detection on this. So faces equals face cascade.detect multiscale. We'll just pass in this new CV image after it's been binarized. And then let's call our show recs faces to see the results. So that's kind of interesting. Not better, but we do see that there is one false positive towards the bottom, where the classifier detected the sunglasses as eyes and the dark shadow line as a mouth. If you're following in the notebook with this video, why don't you pause things and try a few different parameters for the threshold value. The detect multiscale function from OpenCV also has a couple of parameters. The first of these is the scale factor. The scale factor changes the size of rectangles, which are considered against the model. That is the Har Cascades XML file. You'd think of it as if it were changing the size of the rectangles which are on the screen. Let's experiment with the scale factor. Usually it's a small value, so let's try 1.05. So faces equals face cascade.detect multiscale, and we'll pass in our image and 1.05. And now let's render those results to the screen through show recs. Now let's also try this on 1.15. So we'll just put that in there quickly. And then finally, let's try and do this on 1.25 as well. So we'll put that in there. And let's give it a run. We can see that as we change the scale factor, we change the number of true and false positives and negatives. With the scale set to 1.05, we have 7 true positives, which are correctly identified faces, and 3 false negatives, which are faces which are there but not detected. And we have 3 false positives, which are non-faces, which OpenCV thinks are faces. When we change this to 1.15, we lose the false positives, but also lose one of the true positives, the person to the right wearing a hat. And when we change this to 1.25, we lost more true positives as well. This is actually a really interesting phenomenon in machine learning and artificial intelligence. There's a trade-off between not only how accurate a model is, but how the inaccuracy actually happens. So which of these 3 models do you think are best? Well, the answer to that question is really, it depends. It depends why you're trying to detect faces and what you're going to do with them. If you think these issues are interesting, you might want to check out the Applied Data Science with Python Specialization Michigan offers here on Coursera. Okay, beyond an opportunity to advertise, did you notice anything else that happened when we changed the scale factor? It's subtle, but the speed at which the processing ran took longer at smaller scale factors. This is because more subimages are being considered for those scales. This could also affect which method we might use. Jupyter has nice support for timing commands. You might have seen this before. A line that starts with a percentage sign in Jupyter is called a magic function. This isn't normal Python. It's actually a shorthand way of writing a function which Jupyter has predefined. It looks a lot like the decorators we've talked about in a previous lecture, but the magic functions were around long before decorators were part of the Python language. One of the built-in magic functions in Jupyter is called timeIt, and this repeats a piece of Python 10 times by default and tells you the average speed it took to complete. Let's time the speed of detect multiscale when using a scale of 1.05. So percentage timeIt to call the magic function, and then we just write our normal Python code. Face cascade.detect multiscale, CV image, and 1.05. Okay, now let's compare that to the speed at scale 1.15. So same thing, timeIt, face cascade.detect multiscale, CV image, 1.15. So you can see that this is a dramatic difference, roughly 2.5 times slower when using the smaller scale. This wraps up our discussion of detecting faces in OpenCV. You'll see that, like OCR, this is not a foolproof process, but we can build on the work others have done in machine learning and leverage powerful libraries to bring us closer to building a turnkey Python-based solution. Remember that the detection mechanism isn't specific to faces, and that's just the HAR Cascades training data we used. On the web, you'll be able to find other training data to detect other objects, including eyes, animals, and so forth. One of the nice things about using the Jupyter Notebook system is that there's a rich set of contributed plugins that seek to extend this system. In this lecture, I want to introduce you to one such plugin called py-WebRTC. WebRTC is a fairly new protocol for real-time communication on the web. Yep, I'm talking about chatting. The widget brings this to Jupyter Notebook systems. Let's take a look. First, let's import this from the library, two different classes which we're going to use in a demo, one for the camera and one for the images. So from py-WebRTC, import camera stream and image recorder. Then let's take a look at the camera stream object, so help camera stream. We see from the docs that it's easy to get a camera facing the user, and then we have the audio on or off. We don't need audio for this demo, so let's create a new camera instance. So camera equals camera stream.facing user and audio equals false. The next object we want to look at is the image recorder. So help image recorder. The image recorder lets us actually grab images from the camera stream. There are features for downloading and using the image as well. We see that the default format is a PNG file. Let's hook up the image recorder to our stream. So image recorder equals image recorder and stream is equal to the camera. Now the dogs are a little unclear about how to use this within Jupyter, but if we call the download function, it will actually store the results of the camera, which is hooked up in imageRecorder.image. Let's try it out. First, let's tell the image recorder to start capturing data. So imageRecorder.recording equals true. Now let's download the image. So imageRecorder.download. And then let's inspect the type of the image. So type imageRecorder.image. Okay, so the object that it stores is an ipywidgets.widget.widgetmedia.image. How do we do something useful with this? Well, an inspection of the object shows that there's a handy value field, which actually holds the bytes behind the image, and we know how to display those. So let's import pill image, import pill.image, and then let's import IO, and now let's create a pill image from the bytes. So image is equal to pill.image.open, and then io.bytes.io to create a stream, and then imageRecorder.image.value. Wow, that's a lot of dots. And let's render it to the screen. So that's just display image, because it's just a pill image now. Great, you see a picture. Hopefully you're following along in one of the notebooks and you've been able to try this out for yourself. So what can you do with this? Well, this is a great way to get started with a bit of computer vision. You already know how to identify a face in the webcam in the picture, or try and capture text from within the picture. With OpenCV, there's any number of things that you can do. simply with a webcam, the Jupyter notebooks, and Python.